Hey guys, welcome back. We're going to move on into our Pythagorean theorem. So this is something we've actually talked about before with the distance formula, but let's do it again just specifically on the Pythagorean theorem. So this one should be pretty simple. I'm going to show you a lot of really cool stuff. You probably think you already know the Pythagorean theorem, but I guarantee you're going to see some the Pythagorean theorem from a few different angles. It's been around a long time, probably one of the most famous parts. If you think of geometry, you probably think of the Pythagorean theorem, so it's kind of a big deal. So I hope you guys enjoy this. So a question that's actually an application of the Pythagorean theorem is, why do football players always run the sidelines? So as soon as they catch a pass or you have the running back, usually they'll run straight to the sidelines and then they'll run right along the sidelines. You think, well, maybe that would be a bad idea because they can just push you out of bounds. They don't have to tackle you at that point. They just push you. They can push you out of bounds and save a touchdown. Well, the reason they always run the sidelines is because it's always going to be the shortest distance. So this blue line here, if you can run a 40-yard dash in 4.8 seconds, which is really fast, I think. I don't really know, but anyway, then running diagonally across the field is obviously going to be a longer distance, and it doesn't matter where this player is at here. Any diagonal across the field is going to be a longer distance than 12 here. So it doesn't matter even if it's right here. Technically, that's a longer distance. And so you're making all the defensive players have to adjust to you and run a longer distance just to catch up to you and to be able to push you out of bounds. So this is an application of the Pythagorean theorem. So if you can run 100 yards in 12 seconds, which is basically a 40-yard dash of 4.8 seconds, then you could run basically across the field in 6.8 seconds. So how long would it take you to run diagonally across from pylon to pylon? So if we wanted to know that, we would do the Pythagorean theorem. So we have a squared plus b squared is equal to c squared. What's special about our c is it's our longest side. It's going to be opposite of our biggest angle. It's our hypotenuse, and the other two, of course, called the legs. And as you guys already know, what's in between the legs of a right triangle? A right angle, exactly. And then somehow that ties together with the baby daddy rectangle who has the isosceles trap on the side. But anyway, I know it's like a giant conspiracy. Once you see it, you can't not see it. So I'm sorry. Anyway, so plugging in the values, we'd have 6.4 squared plus 12 squared. Now the legs don't matter which one's I guess the left leg or the right leg. It doesn't really matter which one you do because of the commutative property of addition. So it doesn't matter the order that we add in. The one that's important is that the hypotenuse has to be by itself. So that's going to be x squared in this case. And at this point, we can plug that straight into the calculator. So that's what I'm going to do. So we have 6.4 squared plus 12 squared, which is 144. I already know that one. And then that's going to give us what x squared is equal to, which is 184.96. But I don't want x squared, I want just x. So I have to take the square root to undo the square, so that's the half power. If I do it to one side, I got to take the square root of the other side as well to keep it balanced. Alrighty, so I'm going to do caret 0.5, then hit enter. Now if you're using your phone, more than likely you have to type in the number first and then push the square root button, which might be like second x squared. So it's going to be kind of working backwards in how I put it in the calculator here. But you'll have to figure out how you do it. I think the Android and iPhone are pretty much all the same. Where you're actually working backwards. So anyway, 13.6 is going to be equal to x. So you can run diagonally in 12 seconds. The same person would take 13.6 seconds to run diagonally from pylon to pylon. And that's why it's the shorter distance and gives you the advantage over the defense. So where would you catch them? So if this person's running a 40-yard dash here and you wanted to catch them right before they get to the pylon to push them out of bounds, the same distance here running this diagonal, let me see if I can pull up a pen. There we go. Would actually be right here. So if you're at this point here or anywhere on the inside of that line, really on the inside of this arc, then you should be able to as long as you run the same speed as they do, which typically that's not going to be true. The wide receiver is going to be really fast. Then you should be able to catch them before they get to the end zone. Well, what if you don't want to catch them right before the end zone because they can just reach across? So where would you have to set up your defense? So I'm not a football coach. I like watch football, but I'm not like really good. But if it's like Pythagorean theorem football, sign me up, coach. All right. So you imagine if I gave like a halftime speech, like, guys, your angles were terrible. I get a drawing board with like the compass. Oh, I made a joke last year, but I'm not going to make it this year because I'm more mature and the internet's forever. All right, so if we wanted to catch him before we get to the 30-yard line, who could do that? So if we take our compass and we draw our arc from here, the 30-yard line, to our wide receiver, say the wide receiver has the ball, the corner is always going to be able to get to him. That's why it's the primary responsibility. To catch him before the 30-yard line, looks like maybe the outside linebacker could do it. The free safety could as well. Now, if I back this line up here and draw an arc from 15-yard line, then now the middle linebacker technically would be able to get to him before the 15-yard line, but a middle linebacker is probably not going to be as fast as wide receiver, and our strong side safety could get to him as well. Before the 5-yard line, now we're backing this up even more. Now it looks like both outside linebackers and all the linebackers could probably get to him, and both the safeties, and maybe even the defensive end. That would be kind of funny. Can you imagine the defensive end chasing down the wide receiver? Probably not going to happen, but technically that would how it works. So your angles were terrible. All right, so here we have the Pythagorean theorem. Notice when they started out, both of these a squared and the c squared were exactly equal. So over here we have the a squared plus the b squared, and they're going to fill up the c squared on the bottom here, which is like absolutely fascinating. So the area of the a squared plus the area of the b squared gives us a c squared. So this is kind of like a visual, anyway, just a really cool visual GIF of what's going on there. So I hope you enjoy that. So without the animation or the GIF, we could show it like this. So we have 3 squared, which would be 9, and then 4 squared. Again, it's a square with sides of 4. And then 5 squared would be 25. And 3 squared plus 4 squared is 5 squared. This is our smallest Pythagorean triple that we have. So 3, 4, 5. It's really common, we use it all the time. So 9 plus 16 is equal to 25. So it works, kind of cool. All right, so let's look at investigating the Pythagorean theorem here. So this one's actually kind of fun because we can move this point around, and we can see as we increase the length of A, one of the legs, or the length of B, I think, yeah, let me do either one of them, which is kind of cool. You can see how that changes the length of C. Now, they have the links here, A, B, and C marked out, A squared, B squared, and C squared, but these are not actually adding up to each other, and the reason for that is our angle is not actually going to be 90 degrees at this point. So depending on what what's going on here? So depending on what we set our angle to, it's going to change the value for A, B, and C, obviously. So as we increase the angle, the C is going to be larger. As we decrease the angle, the C squared is going to be smaller. In fact, at some points, the C squared would actually be smaller than the other links because it's not a right triangle anymore. So if I set this to 90 degrees, there we go, then it'll actually work. So we have the Pythagorean theorem here. And then as I move these points, they'll always be equal. The a squared plus the b squared area will always be equal to the c squared. There are lots of different proofs for this one, visual proofs. I guess we can step through this one here. Let me increase this side here so it's a little bit larger. All right, so basically they take this triangle and they basically moved it to the other side. And then they moved one down here and then one here. And if you notice, this square here has 4 of those red triangles, okay? And then on the next one, they moved another red triangle there, there, and there. And notice this square here has 4 red triangles here, 1, 2, 3, 4, and then just kind of ignore the overlapping one there. So what we notice is that these 2 squares also are going to be equal to each other. And one of them has the 4 red squares and the c squared. The other one has the 4 red squares and the a squared and the b squared. So pretty much the same proof, just not like animated like that. I can show you as well. So before we were able to do proofs with the visuals and the GIFs and stuff like that, we had to do all of our proofs with constructions like straight edges and compasses, like whatever this guy's playing around with here. It looks like fun, right? We've done some of that with our constructions, and we'll do even more. And I did write a grant. I'm going to write another grant, and I'm so excited. It's going to be awesome. So anyway, this guy is Euclid of Alexandria from around 300 BC. He came after Pythagoras, but he actually kind of organized all of what we knew about geometry at the time and put it all together. And he's known as the father of geometry. So he, proudly wore his chain. I don't know if you can see the little remnant here. But yes, he is an OGT, which stands for Original Geometry Teacher. I don't know what you thought it was. But I also am OGT because I'm originally a geometry teacher before I taught stat. So just so you know. And he was always wearing his chain. And it always, yeah. So even it's there. Don't worry, it's there. So what he's doing, drawing in the sand or drawing on whatever he's drawing on, that's what a classroom used to look like. So we're doing some crazy virtual classrooms where you guys are probably in your pajamas. But he used to have to gather in the town square and listen to this guy draw things in the sand and teach him geometry, which is crazy cool. All right, so again, more compass work, straight edge. They have their rulers and their compasses, just like we've done, which is really cool. And that's what geometry used to be. So their proofs, before they even had algebra and variables, they would have to have basically picture proofs, just like this one. And this is the picture proof, or one of the many picture proofs of the Pythagorean theorem. So if we look at the white areas here, so our beige areas are those four triangles we talked about before. So the A, B, and the C, the A squared, B squared, C squared. So those are going to be our four beige triangles. And this one also has four beige triangles. And then we notice the difference between just rearranging those four triangles will give us a C squared, or the A squared plus the B squared. And those white areas have to be exactly the same, which means the A squared plus the B squared is equal to the C squared. So this would be their visual proof. And all they would do, if they even gave you a hint, is they would tell you, okay, look at the white areas, and then you say, oh, A squared plus B squared is equal to C squared. And then they would say something like A squared plus B squared is equal to C squared, and then behold. That would be like the equivalent of a mic drop back then. Yeah, so mic drop, walk away. They would say behold with an exclamation point. And that would be it. This would be their entire proof, which is kind of cool. So let's break this part down just a little bit here. So I'm going to basically show you two different ways you can set up for the area for the entire square here. So this side length is A plus B. So A plus B is going to be this length for the base, and the height is A plus B. So if I do A plus B times A plus B, that's going to give me the area of the whole square. The other way we could do it is by breaking it down by pieces. So each one of these triangles is going to be a length of A times B divided by 2, because it's 1/2 the base times the height, right? And they're all perpendicular. So there are four of these 1/2 A times B's plus the C squared that we have in the middle. So you can either do area by deconstruction or by multiplying the base times the height. Well, if we do the base times the height here, we end up doing first, outside, inside, last, which is basically FOIL, right? So first would be A squared, inside and outside would be 2AB, and then last would be B squared. And half of 4, or 4 times 1/2 AB is going to be 2AB, and then plus the C squared on the end. So these equations are still balanced and still equal. There's only one step, I don't know if you can see it, but if we subtract the 2AB from both sides, what are we left with on this side? A squared plus B squared is equal to C squared. Oh my goodness, mic drop. Awesome. So stinking cool. Yes, lots of fun. And actually, when we get to class, I can show it to you. It's at the school, and we're like probably snowed in at this point. But anyway, I actually have a little like kind of a board game, I suppose, but little pieces that you can rearrange. And there's like 3 different proofs of the Pythagorean theorem you can use with those 4 triangles and the C squared, which is really cool, and other different links. So I'll show it to you if you remind me. All right, so if the Pythagorean theorem says if it's a right triangle, then A squared plus B squared is C squared. So it's not just this is always true, it only happens if it's a right triangle. And we saw that with the Desmos demonstration. So whenever this was less than that, the C squared was smaller. Whenever this was an obtuse angle, then the C squared was going to be larger than the A squared plus the B squared, which we'll talk about more formally tomorrow. All right, so the converse of the Pythagorean theorem would state that if A squared plus B squared is equal to C squared, then it must be a right triangle. If you remember converse, like shoes on the wrong feet, we just switch the order. So if we look at A squared plus B squared and it sure enough is equal to the C squared, then we know that we must have a right triangle, which will be opposite of the longest side. There you go. So we'll use that to prove whether or not it's a triangle. Then tomorrow we'll prove it's acute or obtuse or even triangle at all. So tomorrow will be really easy, which will be next week, but I don't know when you're watching this video. All right, so let's go ahead and get started on the assignment. So I hope you enjoyed that. There's really not a whole lot of like difficult parts of the Pythagorean theorem, and most of it we're just putting in the calculator. There's some reducing radicals, but nothing too bad. So I wanted to give you just kind of an exciting, or at least I felt it was an exciting demonstration of all the different applications of the Pythagorean theorem, including space math. Oh my gosh, it's gonna be so cool. All right, number 1. So on this one, we want to find the missing hypotenuse length, and then we have 12 and 9. So the A squared and the B squared are going to be our 12 and 9. It doesn't matter which one's which, right? They're just going to be the legs. So I did 9 squared plus 12 squared is equal to x squared. And then I'm just going to put that right in the calculator. So 9 squared plus 12 squared, which is just 144, is going to be equal to 225. So we have 225 is equal to x squared, but I don't want x squared, I want just x. So how do I undo a square? We'll do the 1/2 power or the square root. It's the same thing. So I want to take the square root of that value that I have. So I'm just going to do the following answer, caret 0.5, and that will give me 15. So the square root of 225 is equal to 15. So this length here is 15. And this is a very common Pythagorean triple, just like 3, 4, 5. This is going to be 9, 12, and 15. So we'll see that with similar triangles as well by side, 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 but don't worry about it. We're just going to plug it in the calculator at this point. All right, number 4. So this one's different because we already know the hypotenuse. We're solving for a leg. So we're actually going to be using subtraction. So we kind of have to rearrange our formula. So the shortest side I usually do is a, by the way. So that would be 6 squared plus the y squared is equal to radical 85 squared. Now what happens when we square a radical? Well, a radical 85 squared, or like basically the 1/2 power times 2, is just going to be the first power. So they're going to undo each other. So it's just going to be 85 on this side over here. So what I'm going to do is subtract the 6 squared from both sides, leave me with y squared is equal to basically 85 minus 6 squared. Now the reason for that again is because the 1/2 power of square is going to be 1. Remember, they undo each other. So basically it just goes to, in other words, like if we square 85 squared, rad 85 squared is going to be just a regular 85. So over here we had 6 squared and then y squared, and so we just subtract 2. All right, so y squared is going to be the difference between those two. So I'm going to plug that in the calculator. So we have 85, 6 squared is 36, right? So 85 minus 36 is 49, and then we take the square root of that, which is a perfect square, so you should probably be able to do it in your head. So we have y squared is equal to 49, so we take the square root of both sides, and that leaves us with y is equal to 7, which should be on your answer bank. All right, number 9, we want to find the value of x expressed in the simplest radical form. So we are going to be reducing radicals on this one, so make sure you remember how to do that. Again, we're solving for a leg, so we're going to be doing subtraction, not really adding. We just have to change the order. So I think I do 4 squared plus x squared is equal to 18 squared. First step would be to subtract the 4 squared from both sides. So just like before, we're going to do 18 squared minus 4 squared, which we can plug that straight in the calculator. So 18 squared minus 16, or 4 squared, however you want to put it in. All right, so that's 308. So we have x squared is equal to 308. And then I want to undo the square by doing the square root, and so do square root of both sides, and then break this down. Well, I see this as an even number because it ends in an even number, so I can divide it by 2, and when I do that I get 154 and 2, and then 154 is also even again, so I can take out another 2, which leaves me with 77. 77 actually is not prime. It breaks down even further, but it breaks down to 7 and 11, and then both of those are prime. So if I notice I have a common pair of 2's that can come out in the front, so I'm going to be left with 2 and then multiply these back together, so 2 radical 77. Number 13, use the converse of the Pythagorean theorem to see if the triangle is a right triangle. So the converse says that if a squared plus b squared is equal to c squared, then this must be a right triangle. So let's check. So a squared plus b squared would be 8 squared plus 15 squared, and I want to check and see how does that relate to the 17 squared. So in the calculator, we're going to do 8 squared plus 15 squared, which is 289. And then I'm going to do 17 squared, which is also 289. So they are equal to each other. And so we have 289 is equal to 289. So that means that this must be a right triangle. So therefore, by the converse of the Pythagorean theorem, this is a right triangle. So that angle must be 90 degrees, the one that's opposite of the longest side. All right, 19. For each pair of numbers, find the third whole number for each of the 3 numbers that form a Pythagorean triple. Okay, so I went ahead and gave you the diagram to make it a little bit easier. If it's Pythagorean triple, then we know it must be a right triangle, so we can use the Pythagorean theorem. So we're going to do 13 squared plus 84 squared, and that's going to be equal to x squared. We're just going to plug it right in the calculator. So we have 13 squared plus 84 squared. And then we're just going to take the square root of it, right? So that's going to give us this number is equal to x squared. Take the square root of both sides. So again, just put that in the calculator. I'm going to do caret 0.5 power. It's my favorite way to put in the square root, which gives me 85. Okay, so it is a Pythagorean triple because all of our answers are whole numbers or integers, they're not going to be radicals. So we call those Pythagorean triples, by the way. And we like to use them because it's nice when it comes out as a whole number. All right, so 84, 85, and 13 actually works kind of nice. All right, so what's the missing one here? Well, if you notice on this one, we're subtracting. So what's going to end up happening on this one when we rearrange it is we're going to end up subtracting the 12 squared from both sides. So it's going to be minus 12 squared, minus 12 squared. And so you don't have to set this up. After a while, you can pretty much figure out how you're going to do it, right? So we're going to do 20 squared minus 12 squared, and then take the square root of it when we're done. So 20 squared minus 12 squared, and then take the square root. It's just really the same pattern we're doing over and over again, which leaves us with 16. So the missing angle x is equal to 16. All right, so a fun, just kind of teaser on number 26. This is like space math, and it's gonna get so cool. We'll do a lot more with space math when we get to tangents and circles, but oh man, one of my favorite topics that we get to do because it's literally NASA math. All right, so let's say that we have the Earth, which is round, in case you didn't know, and Tide Pods will kill you. And put down the paprika if you're watching the video. Anyway, so 6,370 kilometers is the radius of the Earth, and all of its round glory. And then let's say that we are 350 kilometers above the surface of the Earth, and we're in orbit. I think the International Space Station is like 200 kilometers, so this is pretty far out there, so we're not going very fast. Space math. Anyway, so the question is, how far can we see to the horizon, which would be like the vanishing point of where we can't see anything beyond that point. If I extend this line here, basically at this point you could see, but you wouldn't be able to see anything curving past that because the world is sure enough round and not flat. You can't see everything from any perspective, no matter how far away you are. Okay, so we have a right triangle because these tangent lines are going to be perpendicular to the radius of the Earth, and then we want to solve for how long you can see, which is one of our legs. So when we plug this in the calculator, small leg is going to be 6,370. Our other leg is x, and then this we would add those two together, which would be 6,720. Yeah, okay. So basically we subtract this from both sides, so we get x squared is equal to the difference in those two. I'm just going to put it right in the calculator because it's going to be a big number. So 6,720 squared minus 6,370 squared, and that's going to give us that number. And then just like before, we take the square root of it, right? So caret 0.5, oops, didn't mean to do that, 0.5, and I have to delete that part. Okay, cool. So we're gonna be able to see a distance of 2,140 kilometers. So we took the square root of that value, which was a really big one, 2,140 kilometers, which is about a third of the radius of the Earth. So obviously this is not to scale. If I drew it to scale, this length here would actually be probably about right there. All right, so I rearranged this so it's closer to scale. So if this is the radius of the Earth, that's about how far we'd be able to see, which is about a third of the radius of the Earth. So they're still not quite right, but it's close. So that's really how close relative they are. That's even further than the International Space Station. So they're actually really close right off the surface of the Earth. But spoilers, you didn't see that. You didn't hear that from me. All right. If you guys have any questions, please let me know. If not, I'll see you guys later. So have a good one.